Hi there! Have you ever thought of using an Arduino as an audio oscillator? For example, to play an alarm sound or to generate notes using it as a musical instrument. Today we will explore a couple of techniques that can be used to do just that. Let's begin! Let's start with a simple square wave generator, but rather than making it emit a single tone, we will do something a little more sophisticated by controlling the pitch of such oscillator using a potentiometer. Let's begin by taking a look at the schematic to do that. This one on the left is the potentiometer that will be used to select the pitch. It is used as a simple voltage divider. One side is connected to ground, the other side is connected to the plus 5 volts reference voltage provided by the Arduino itself, and the central cursor is connected to analog pin A0. Such pin will allow the Arduino to read the current voltage of the cursor, convert it into a specific frequency, and then emit a square wave of such frequency on one of its digital pins. For that, I have used the digital pin D2, which will be set as a digital output. Since the digital output will provide a signal that can be either 0 volts or 5 volts, the square wave on this output will contain a DC component of about 2.5 volts. Capacitor C1, along with the resistor R2, is there to act as a high-pass filter with a very low cutoff frequency, which will basically only eliminate the DC component, leaving unaltered the actual square wave. Resistor R1 is there just to limit the current that can be drawn from the Arduino pin. We don't want to burn the circuitry on such pin, trying to extract a current beyond its capabilities. Because of R1 and R2, the output square wave of this circuit will have a high impedance. If we needed a lower impedance along with a higher current, we could still add an impedance adapter in series with the output of this circuit, for example an op-amp in a voltage follower configuration. And that's it, we don't need any other component to make the Arduino play a sound. Let's now take a look at the software that will be needed to make this circuit work. First of all, note that the software is so simple that we don't even need to put anything in the setup function. Then let's take a look at the loop function. It is very simple. There is a variable named frec for frequency that holds the frequency of the signal emitted by the Arduino. The variable is set by calling function readFrequency, which takes care of examining the voltage available on A0, which is given by the potentiometer. We'll look at this function in a moment. Once the frequency is set in the variable, we can call function tone, passing to it the pin number through which the signal should be emitted, and the frequency on the signal itself. Function tone is an internal function provided by the development environment of the IDE. As a result of calling tone, the Arduino starts immediately emitting the square wave at the specified frequency and continue to do so until we change the value of the frequency, or until we tell the Arduino to stop, using function noTone, which we are not using in this application since we want to always emit the tone. After calling tone, there is a call to function delay, passing to it the value of 1 millisecond. This call is not necessary for making the program work, however, it is needed for stability. If we did input this call at the end of the loop would run too fast, preventing the Arduino from taking time to generate the tone. Let's now take a look at function readFrequency, which is toward the beginning of the file. This function does just one thing, accessing the voltage present at pin A0 and passing it to an internal analog-to-digital converter. The converter gives back to the function a 10-bit value proportional to the voltage on pin A0. Being a 10-bit value, it can go from 0 to 1023. However, if we just passed this value to the function tone, we would only be able to emit a frequency between 0 and 1023 Hz. The problem is that the tone function cannot generate a frequency smaller than 31 Hz, and that is why we add 31 to the output of analog read. Also, since we want to reach a higher range of frequencies, the output of analog read is also multiplied by 4, which is the value of the constant frec adjustment. After all these calculations, the actual range of frequency will now be between 31 Hz and 1023 times 4 plus 31, or 4123 Hz. Note, however, that this multiplication causes a problem. We will not be able to emit certain frequencies. For example, when the output of analog read is a 0, the frequency is going to be 31 Hz, of course. When the output of analog read is 1, the frequency is going to be 1 times 4 plus 31, which is 35 Hz. And you can see now how we cannot generate any of the frequencies in between 31 and 35, I mean 32, 33 and 34 Hz. And the same will happen also in any other interval, and at higher values from analog read, we correspond larger gaps in the frequencies. However, since the multiplication factor is only 4, we should not be able to notice the gaps with our ears. One way to avoid the gaps and reach higher frequency would be, for example, to input the value as a binary value at the remaining digital pins of the Arduino rather than using a potentiometer, but that would consume most of the pins just for that. Let's now go to the lab and use an actual Arduino Uno to build the circuit and test it along with this program. Okay, I just uploaded the code onto the Arduino Uno on my testing board. Here it is, and basically this is the circuit that we just described. We have basically just the Arduino. There is this potentiometer that is connected here to the A0 connector, and then the output is taken on D2 and goes to this capacitor and these resistors, and basically pick up the signal from the oscilloscope probe. This is the potentiometer that deals with updating the frequency, which we read continuously from the Arduino. And so moving this potentiometer we can change the frequency. And let's see what we have here on the oscilloscope. Let me zoom in so you can see better. Here we go. And so you see, if I move the potentiometer in one direction, the signal lowers its frequency. We go down to 30 Hz, as you can see. And then on the other end, we can go up, 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 until we reach the maximum for this circuit, which is about 4.1 kHz. So this is the best we can do with an Arduino Uno connected the way we have seen. The other thing we can do is to use a amplifier to actually hear the sound, and let's do it right now. This is the power supply that I'm going to use for the amplifier, and here we are back on the bench. The power supply. Let me connect the power here, and then I can attach, actually what I can do is just take the signal from the oscilloscope and put it instead over here. So now the oscilloscope probe goes directly into the amplifier. Let's set the volume to the minimum. Let's turn on the power supply. Okay, and now we can hear what's going on. Increasing the... Okay, let's change the frequency. This is the minimum, so the 30 Hz. Then we go up. And you see we can have a continuous adjustment of the frequency very easily. Now that we have seen how easy it is to generate a square wave in the audio range, let's think for a moment on how we could obtain a different shape, like a sine wave or a triangular wave, for example. One way to do that is by adding additional components to the circuit to filter out all the harmonics but the base one, so we can obtain a sine wave, or we could use an integrator to obtain instead a triangular wave. Doing so, we are basically adding analog circuitry to what we already have. But is there a way to obtain different shapes just by acting on the software? Well, actually yes, but I'm not sure if the Arduino Uno is capable of handling that, if it is enough powerful. So let's figure it out together. What I would like to do is to use a so-called wavetable. Let me show you. I used a spreadsheet to calculate samples of 3 different shapes at different times. Basically, at time 0, I have a triangular wave that in that moment has an amplitude of 1.25 volts. Then I have also a square wave with an amplitude of 2.5 volts. And finally, I also have a sine wave with an amplitude of 1.25 volts. At the time t equals 1, taking new samples of the above waves, we obtain these new numbers: 1.32 for the triangular wave, 2.5 for the square wave, and 1.37 for the sine wave. Then I take another sample of the 3 waves at t equals 3, and so forth until I have taken samples across the whole period of all 3 waves. Here is a picture that exemplifies the concept for a sine wave. In my case, I have used a period divided in 64 parts, from t equals 0 up to t equals 63. Now that we have these numbers, I can draw a graphic that has on the x-axis the time, and on the y-axis the amplitude in volts. I can take all the points on this table to the chart, and then I can connect all the dots. Here is what I obtained doing that on the wavetable of the spreadsheet. And look, the representation of those numbers in the table provides us the diagram of the 3 waves we selected. The point now is to replicate this procedure on the Arduino with an appropriate software. I will need to write some code that, based on the frequency obtained through the potentiometer used in the previous circuit, will calculate the time in between 2 samples. Such time will need to be measured in microseconds to be able to deal with waves in the frequency of thousands of hertz. At every interval, we will need to read the amplitude of the sample from the table, and somehow we need to create an output voltage of that amplitude. And we could do that simply using multiple digital output pins rather than one, so we can define the various voltages we need as a binary number. And we can use these digits as the inputs of a digital-to-analog converter, like for example an R2R ladder. The output of the DAC should provide us with a particular wave shape associated with the samples we were using. Does it seem complicated to you? Well, yes, but not that much. My main problem is that the Arduino will have to do fast readouts of the wavetable and also fast calculations based on those values. But will the Arduino be able to do that? Before writing this complicated program and then discover that the Arduino is not able to make it, let's try some experiment with a simple square wave. For the square wave alone, the wavetable is made up of 2 values only, the high value and the low value of the square wave, and we can use a single digit to represent it, a 0 and a 1. If the Arduino can handle that, then we can try using multiple samples to generate a sine wave and a triangular wave, otherwise we won't need to waste time trying to do something that is not possible. So let's try first to replicate the square wave using this technique instead of the tone function, and see if that is feasible, and then we will go on from there. Here is the schematic of the circuit to do that. Yes, it is the same schematic we used to generate the square wave with the tone function. The fact is that to generate a square wave using a wavetable, we only need 2 values in the table itself, and to represent 2 single values we just need a single digit. We don't need multiple digits like we would if we were generating a sine wave or a triangular wave. And so we will use the same circuit. This time, however, once we read the value of the voltage of the potentiometer and we determine the frequency, instead of using the tone function, we just write a 1 on the digital output, then we wait for half period of the wave, then we output a 0. We wait again another half period, and then we go back writing a 1, and so forth. Let's write a program that does just that. And here is the program. This time we do use the setup function to initialize pin 2 as a digital output port. and we also define the first state of the square wave we want to generate, in this case a high, representing the 1. The digital output will just have to flip between 1 and 0 continuously, or high and low. And it does have to do that at the rate that is imposed by the requested frequency. So in the main loop, we read the frequency value like we did before, then we determine the next level the square wave is supposed to have. If it was a high, it has to be now a low, and vice versa. Once we determine the level, we output it through the call to digital write, passing the pin number and the actual level, here called wave state. At this point, before restarting the loop, we need to wait an amount of time equal to half the period of the square wave. To do that, we determine the length of such pause in microseconds, based on the frequency that was determined earlier, and then we pass this time to function delay microseconds, which will prevent the loop from restarting for that amount of time. This will make the Arduino generate the square wave, but will the Arduino be fast enough to do that? How high we can go with the frequency in such a case? Note that in the first case, using the function tone, we just asked the Arduino to generate the square wave internally, using its hardware. Now, instead, we need to execute the code in the loop. And how long will it take for each instruction to execute? Will the execution be fast enough to let us reach reasonable frequencies? Keep in mind that this is an experiment. If the Arduino won't go to frequencies in the tens of thousands of hertz, there is no way that we will be able to reach even just 1000 hertz with a sine wave, for which we will need to complicate the program to deal with several digits, not just one. Like for example 6 or 8. The generation of the sine wave will be 6 or 8 times lower because of that. So let's move to the lab to see if we can find an answer to these questions. Okay, this is the new program for the Arduino, and so let's install it. It's uploading now. Okay, and now let's take a look at the oscilloscope of what's going on. Remember that this circuit has not changed with respect to what we did before. It's exactly the same one, and it's has the oscilloscope still connected over here, so we just need to go over there and see how it behaves when we move the potentiometer to control the frequency. And look, right now we have a frequency of about 1.25 kilohertz, and the potentiometer is all the way on the right though this time. Like before instead with this same position we had about 4 kilohertz, so we are not driving enough the Arduino. Let's see if everything else works fine. So let's try to rotate to the left the potentiometer and let's see what happens. And yes, the frequency diminishes correctly. So we go to a minimum, which is 31 Hz again, and then we go up, and the maximum here is 1.25 kilohertz. So it's not enough, so it looks like the frequency adjustment multiplicator has to be increased. Let's do that right now, and let's see what happened. So I'm gonna modify this. From 4 I will move it to 6. We should have an increase of 50% of the maximum frequency this way. Let's see if that's true. So let's build and download again and upload again. Done uploading, and here is a new frequency. Oops, look at that. It went from 1.25 to 1.56 kilohertz. Not much of a change, right? Let's try to go up again, and still works, of course. But now let's try to go up again. Let's see what we can get. So this time I will move the adjustment to 10. Look at that. Which is much higher now. So let's see what happens this time. Building, uploading, done. And yes, we have increased again but it doesn't seem the increase to be substantial. Now we have a 1.95 kHz, so we are still below the 2 kHz. And now the multiplicator is 10, which means that the frequency for just one single bit changed 10 times more than it was supposed to. Basically, this way we are going to have many gaps in the range of frequencies, much more than we had with the previous program, and so this is not good. In fact, with the other program, it was just a matter of setting the frequency with the potentiometer. If we do it now manually, maybe we can do something better. Let's see, let's give it a try. So let's see what we can do with this. Instead of adjusting the frequency, I'm gonna do something like this. I'm gonna comment out this line, and I'm gonna add a new return value with a maximum frequency, let's say this time of 4 kHz. There we go. Let's see what happens now. So, build and upload. Done uploading. Oh, look what happened. We are stuck at 9.67 kHz. We are not even 2 kHz. So something with this program doesn't work the way the other program that was using the tone function worked. And this is reasonable because we are now trying to do things basically one instruction at a time, all in software. And the software has its limitations because it cannot go too fast. To make it go faster, we will need to increase the clock frequency of the Arduino, which is just 16 MHz, cannot do more than that. The tone functions instead uses another approach, but enables some internal functionality of the Arduino and does this kind of frequency generation in hardware, so you can go much higher than this. You don't believe me? Let's take a look. So let's go back to the previous function and let's open it up. Let me fix a frequency now, like I did with the previous program. So I'm going to comment out this one, and I'm going to add here return. And look, I'm going to put 10,000 Hz right now, 10 kHz. Let's see if this works. I bet it does. So let's upload. Done. Look what we have here. It's about 10 kHz. You see, it's right there. So, and this is because this is in hardware, not in software. The software is just one single instruction to enable the hardware to create such a frequency. Instead, doing it with software limits the possibilities because the software is much slower than the hardware itself. Well, not exactly what I expected. I hoped to be able to go at least around 10 kHz with the use of the wavetable, but it looks like with the Arduino Uno it is just not possible. It is too slow to process the software instructions. But since I really want to generate sounds using a wavetable, I will keep digging to see if I can find other solutions to the problem. Maybe some other and faster Arduino boards, or maybe I could try to use a Raspberry Pi, possibly with a stripped down version of the Raspberry Pi OS, or maybe something completely different. We'll come back to that soon with more videos on this topic, so stay tuned, and in the meantime, happy experiments!